Hello, everyone, and welcome back to the Hyperthesis. We are very excited to be starting season 7 of this podcast, and we're coming to you with episode number 85. We had a nice extended break, and now we are ready to get the season started. I'm Patrick.
I'm Pheely.
And I'm Liam.
So, as I mentioned, this is season 7. It's crazy that we've done 7. We're on our 7th season. We've already completed 6 seasons. If you haven't listened to our previous episodes, I would highly recommend going to check those out. If you have a favorite topic you want to search, just feel free to search that, and chances are we probably talked about it if it's physics or remote sensing related. We've also had a lot of very interesting guests last season, and this season we hope to have a few more guests that we're getting in the works. I wouldn't do any spoilers right now, just so as not to tease you too much. But because we've had such a long break, it's been a couple months since we last recorded and posted an episode. I think for this episode, we're going to do things just slightly differently and just give you a kind of general update of where we are in our research. So all of us are now in the 4th year of our PhD, and I imagine some of us are trying to at least finish in the next year or two. We'll see how that goes. But with PhD comes a lot of different research and unique opportunities, and we've had a full summer of those. So let's start with some updates about what did everyone get up to over the summer.
Well, I guess I can go first. I think this summer has been quite tumultuous for me. I think I did a bunch of things, and sometimes really not related to research. I went home for a month, a little bit, just working remotely, and also visiting family and such. And I'm making some changes in my life a bit, so to accommodate my trying to finish my PhD. So I basically went on a so-called spiritual journey, let's say.
Oh, what did you learn on the spiritual journey?
Oh, many things. How to deal with, trying to finish a PhD. And I think we're getting to a point in life that, well, in a sense, we're still pretty young, but there's a bunch of things I need to figure out. And I think I spend a lot of time trying to figuring those things out. It sounds very vague, but I think a lot of things were just personal stuff that I had to deal with. And yeah, I think I'm in a good spot now in terms of where I am. So I spent a lot of time in the past few months just cracking on my research, because sometimes it feels like you're hitting a wall, and I think we're breaking that wall a bit now. So I think I started seeing the light, so I'm moving towards it. I think I will go into more detail in terms of my research and stuff later on.
It's always a good
that's
feeling.
Pretty much my summer.
How about you, Patrick? What'd you get up to?
Well, I guess just to talk on the personal side very briefly, I got engaged in Nova Scotia. So that was pretty fun.
Congratulations.
Thank you.
Congrats.
I saw that. I judged your choice to get engaged near Pictou a little bit, but you know what?
I mean,
to each
it was
their
on
own.
The beach. And
yeah, I know. I'm just messing with you. Don't worry.
It was on the better side of the harbor anyway.
It's just because I'm from there, I like to make fun of it. But
I went to a wedding a couple of months ago in New Glasgow, so it's pretty good.
You guys have been in my hometown basically more than I have in the last year.
I mean, it's. I was actually in Trenton. You should definitely check out the food truck by the rec center there. It's pretty good.
They have a food truck?
Yeah, they have a couple food trucks there.
Couple?
In the summer.
I knew they had one, but it was more like a stationary food truck.
No, they've got like a couple now where they go like every certain day. But
When
moving
I,
on from that.
when I was a kid, we had to walk down there. No, I'm kidding. Um,
To get
anyway,
Sam's Pizza.
well,
Um, but yeah, so on the research side of things, it was a pretty busy summer. I was again working with the Canadian Forestry Service. So that was pretty fun doing some northern forestry research. It included kind of doing some field work and measurements of trees within the field. There was a lot of work with visualizing forests and the data that we have. So, one of the primary components of that was developing uh, a forest twin or digital twin, as they're known as, to try and represent the forest, but in virtual reality. So, I was working with virtual reality headset and using Unreal Engine to try and bring that data to life.
Actually, when I went to the mass conference this summer, there was this very good talk on the digital twins. And I didn't know what it was before. Apparently, it's like you said, it's basically you create a model that's is in real time, take data from the real actual data, and basically being a twin, but in a model to try to predict what happened next. But instead of having an initial condition or data that's just once, now you take constant stream of data, real data, so you can adjust everything in real time. And apparently, that's gonna be what's gonna be what's called the latest models of things, the most accurate things, right? Because you always get the latest data, and it's a growing field. I heard.
Absolutely. It's really quite a big field, and the more conferences I go to, the more and more papers and presentations there are about digital twins. And they are really useful because it allows you to one try and model what's going on within, say, an environment. So there's giant projects going on to create different types of digital twins, whether it's on a global scale or a regional scale or a smaller scale. And they're just trying to take all this data, as much data as they can, really, and then just incorporate it and essentially view it all in this digital twin and see how it progresses over time and a whole bunch of other stuff. But in this case, the digital twin was mostly for visualization purposes, mainly because I'm not a game developer. So it was more so, okay, you can point at a tree and you can find out what that tree is, but it's based on actual data that was collected. That was pretty exciting. And then, of course, making progress with my PhD using different remote sensing methods to try and measure different forest types and still trying to figure out ways in which we can measure biodiversity. So I've also was fortunate enough to get some nice samples from the field. We're in the process of getting them used and ready for eDNA extraction or environmental DNA, which I've talked about many times before. Yeah, so a lot of exciting things, not all of which I can actually talk about, just some of it's under wraps, but yeah, a couple cool things going on for my summer of research. What about you, Liam?
I did somewhere, let me think, somewhere in between you and Pheely where I didn't do quite as much research as maybe I should have. I did, a lot of personal stuff this summer, but also I did get a good amount of research done. So, um, yeah. So what did I do this summer? On the personal side, I did not get engaged, but I did go to the World Pipe Band Championships and compete there. Just the next best thing, of course. Uh, so we went and we competed and we came second in our respective grade at the European Championships, and then we came fourth at the Worlds in our grade. So my band this year has been moved up to grade 2, which, if you don't know pipe bands, which you probably don't, that's like what is like the league before the NHL in hockey?
Like Division One type.
Yeah,
Like
or
I
what?
don't know about hockey, but like in sorry, soccer,
Yeah,
it's that would be like
Mm-hmm.
Division One, right? Before or like the Championship League
yeah,
thing.
whatever like the most popular league is in any sport. That's grade 1 in piping, and grade 2 is the league that comes before that. So we're not officially a grade 2 band yet, but we're going to be, I'm sure, starting soon. So we're moving up in the world.
I mean, like, if you're grade one, does it mean like everyone has to be like full time? Is it that competitive
No,
where
no,
like everyone has to be full time?
no. You just
Because you
have
don't
to.
see
You gotta be
NFL
good.
player doing that part time, right? Like,
Yeah, it's different because you don't have millions of people funding pipe band competitions, so it's a very expensive hobby. And a lot of people who are in grade one bands, they do it full time, but they don't like compete full time. They make a business related to bagpipes, so they'll like have their own shop or their own repair or their own teaching school or whatever. But a lot of grade one players just have regular jobs. Um, and even in like lower grade bands, there's people who've made livings off of it, right? It's not really like sports in that sense. But anyway, we did that, and um, at the beginning of September, which isn't really the summer, but it's close enough for me, I went to the UK to visit the University of Southampton and the University of Nottingham to kind of talk to and collaborate with some physicists and mathematicians. So that was pretty fun. So yeah, that was kind of my summer, quickly summarized. I'm sure I'm forgetting something, but
So, as a question, just generally for everyone, in terms of the research that you did this summer, do you have anything that was kind of the most impactful, or did you see a presentation or read a paper that was really kind of either just changed your view even slightly of your research, or really helped accelerate it or change direction in a certain way?
I know Pheely's research probably changed direction. But I'll go first because mine changed direction a bit, but only like one of the projects I'm working on. Uh, so Patrick, you might enjoy this one. It's all about waves, which you took a whole course on at some point, which I'm extremely jealous of. But um, so I have like kind of three main research projects going on right now, and one of them is about taking Bose-Einstein condensates and putting them in traps. So you like, trap it between two walls, and then you turn the walls off and let the BEC expand outwards due to the repulsive contact interactions between all the bosonic particles. Um, and then you see what happens. So that's like a super well studied problem in ultra cold physics. But I'm kind of approaching it from a slightly different point of view. And yeah, I've talked about Bose-Einstein condensates before in my research, especially in like the first episode we did. Although that was a long time ago, so things change and you learn more about what you're doing. But that's like if you want to learn about Bose-Einstein condensates and stuff like that, listen to that. I don't want to spend 20 minutes talking about what a BEC is right now. But so I've been learning in order to kind of go down this path. So what am I doing with an expanding Bose-Einstein condensate? I'm just trying to like do math, um, come out with some theory that matches the experiment and simulations and whatnot. So I do all this other research on like black holes and stuff, but right now this is kind of what I'm most excited about because it's I don't know, like all this black hole quantum stuff, catastrophe theory, all these things I research, it's pretty hard. And this when I'm focusing just on one thing, just on something that's only quantum mechanics, there's no catastrophe theory, there's no relativity to worry about. It feels really easy. I'm like, oh, this is great. I don't have to think about reference frames, and I don't have to think about violating Lorentz invariance and all this other crazy stuff. So I don't want to say it's easy, but like it's way more well defined, and I'm having more fun doing it because of that right now. Although the harder stuff can be fun sometimes, but this is pretty good. So there's this thing in hydrodynamics called the dam breaking problem, where imagine you have like the Hoover Dam. At the top of the Hoover Dam, you have a reservoir of water, and at the bottom, you have a reservoir of water, but it's way lower in height than the top reservoir. The dam separates them. Dam breaking problem is just like what happens if you break the dam. What happens with the hydrodynamics of the fluids? How do they evolve in time? Um, so I'm kind of studying that, but in an ultra cold quantum fluid. So you have the something. Imagine the Hoover Dam, and at the top of it, you have a reservoir of water, and then at the bottom of the dam, you have a reservoir of water, but it's way lower in height than the top reservoir because the dam separates them. The dam breaking problem is basically what happens if the dam breaks. If the dam suddenly disappears, and now the top part of the water is allowed to flow downwards into the bottom water, um, due to all the force of gravity and whatnot pushing it down. Uh, what are the dynamics of that? How does the water evolve? Do waves form in it? What happens? So in hydrodynamics, this is a really big problem. I say problem as in like people have figured it out pretty well by now, but there's still things people are doing with it because dams are very important and sometimes they break. Turns out, somewhere in the world, all the time, a dam breaks. And if you can accurately predict and model what that water will do behind the dam, then you can avoid like it flooding into people's houses. You can build kind of these paths that help redirect the water as like a fail safe in case the dam breaks and things like that. So in classical hydrodynamics or fluid mechanics, this is a really popular, well-studied problem, but it turns out it's mathematically very difficult because in fluid mechanics, you have to solve the Navier-Stokes equations, and those are these like coupled nonlinear partial differential equations that you can really only solve in very, very, very idealized specific cases that aren't necessarily realistic. Um, so if you can solve the Navier-Stokes equations in general, you will win a Nobel Prize for that because that's a really hard problem that people have been trying to figure out forever. Um, but so there's ways around it that I won't get into. But I'm studying kind of a dam break problem in a Bose-Einstein condensate. So because Bose-Einstein condensates are really, really cold, they don't have all of these messy things that like a classical fluid would. Like a classical fluid will have turbulence and all kinds of other messy stuff, surface tension, things like that, which on some scales don't necessarily matter, but on some scales they do. In a quantum fluid, everything's kind of nice in the sense that you have this super idealized thing that happens that you'll actually see in an experiment. And the other nice thing is that in an experiment, you kind of have really precise control over these quantum fluids. You can kind of make them do whatever you want in some sense. Yeah. So my take on it is that when people study fluids, you can get things called rarefaction waves, which are like waves of density, and you can get things called dispersive waves, which are kind of like sine waves that they're like surface waves on the back of a fluid. And at least in the dam break problem, in classical hydrodynamics, most people don't really care about the dispersive waves yet. So they care about them, but you get them numerically and then analytically. Only I've seen like one or two papers, maybe three, that try and come up with an analytic model for dispersive waves in the dam break problem. Um, and then in a BEC, people have studied dam break problems or things equivalent to dam break problems, but not near as much. There's only a few papers on it. And again, they do this thing where they only look at rarefaction waves in the water, these density waves. They don't actually look at the surface waves. Um, they do numerically, but not analytically, which means like coming out with some math to match it. So I figured like, oh, I can do that. So I'm attempting to come up with an analytic model for these dispersive shock waves that can form in the dam break problem in a Bose-Einstein condensate, and then maybe in a classical fluid one day. People have done it in a classical fluid already, but I don't like the way they did it. I think you can do better. Uh, but that's a whole other topic. So so this summer, one of the highlights was that I successfully came up with a model for a particular class of this dam break problem, but it's a very like specific idealized class. So I want to generalize it a bit more, which I'm trying to work on now. And I'm actually working on trying to write up a paper for it. I just started like a few days ago trying to write up my version 0 of that. Um, but I'm having a lot of fun doing it because I don't know, I really like fluid mechanics. I wish they taught it in undergraduate more because like when we did undergraduate, they kind of just skipped over it, right?
everywhere because I think fluid mechanics is quite complicated.
Yeah, well, you should be teaching it because of that, I think. Like, you learn quantum mechanics and relativity before you learn fluid mechanics. It makes no sense.
But those are linearized, right? Like I think fluid is less linear.
Well, they're linear in some sense, but yeah.
I agree that I wish we had a fluid mechanics class in undergraduate as well, but I think it would have been cool to do it similar to how we were taught thermal and kind of statistical mechanics, where it was a lot of theory, but we also got to apply that theory to like different simulations and numerical simulations. Um, and I say that partly because former guest of the show, Taya Vice Gibbons, she just completed her candidacy exam, but during her public portion of the presentation, she goes a lot into the different types of fluid simulations that you do based on the theory behind, well, how fluids interact and how they move and like different salinity and temperature and all of that within ocean models, of course, but um, as on a large scale, so on a small scale for fluid mechanics, which is really quite cool. And I mean, there's a lot of very fascinating stuff in there.
Yeah, like fluid mechanics appears everywhere. Like you use it in astronomy a lot, in condensed matter physics, even though you aren't necessarily doing necessarily fluid mechanics. It turns out that like in some regime, your different the equations you're solving look like fluid mechanical equations. Even like a Bose-Einstein condensate, like there's a hydrodynamical form where they look exactly like your hydrodynamic fluid equations, except with like a quantum correction, which you can often ignore, which is actually what like people do in this stuff I'm studying. If you ignore that quantum correction, you get these rarefaction waves, but not the dispersive waves. The dispersive waves are kind of, I don't want to call them quantum waves, but they come from this term that's proportional to Planck's constant. So they come from like a quantum term in some sense. And that even in like relativity, there's like hydrodynamical approximations to the differential equations that they use. I kind of seen it that like everywhere you get, there's always some kind of like fluid mechanical interpretation of things, and it's not like full Navier-Stokes, but they're called the Euler equations, which are, I mean, there's about 12,000 Euler equations out there, but like they're the fluid mechanical Euler equations, and they're approximations to the Navier-Stokes equations that you can actually kind of deal with most of the time. And yeah, I don't know. I see fluid mechanics or some version of it everywhere, and it's like why hasn't this been taught? I mean, we learned about it a little bit during our undergraduate degree, but not much. Like I remember we learned about it for maybe a couple weeks in one of Carl's classes.
I mean, fluid mechanics is like I don't know because in the standard undergrad curriculum, like is it like a fundamental conceptual thing though, right? Like what exactly you learn conceptually?
Mm,
A lot of things you learn like quantum mechanics to relativity is very challenging conceptually to like try to understand that. But fluids is a bit obvious, but a lot of effects of fluids are quite like hard to figure out why is it flow this way or why is the rate. But
well,
compare in terms of complexity of conception, uh,
in like
conceptualization.
in like electromagnetism, though, you learn about like all these fluxes and Gauss's law and surface and volume integrals and all this stuff, and it's like you could learn that stuff in the context of fluid mechanics. Um, maybe electromagnetism's a better spot for it. It depends, but it just feels like it feels like an important branch of physics to just glaze over. Like I'm trying to like because like we had a few like I'm trying to think. Is there any courses that we had that like weren't necessarily extreme? Like we took some electronics and circuits classes, and like those are pretty useful. But I would have liked to swap out one of them for a fluid class.
Yeah, but I would argue that fluid as a like a fundamental class is not as useful as those classes you mentioned in terms of like in your physics career because you can get by without knowing fluid mechanics at all.
Oh, like, it's all
Well,
like
not
depends
at
on what
all.
you do, right? It's super dependent. Like
Yeah,
for most people I know, they took a circuits class. Well, I took a circuits class and then an electronics class. Most people I know wouldn't have needed that electronics class. You could have, and they would have done better off with fluid mechanics. But that's because I know people who do what I do or something similar. Like, if you're doing experiments, the electronics class would be way more useful, I'm sure. So it really depends, I guess.
That's definitely an issue of like a smaller university is you don't have those opportunities to specialize. Whereas, for example, the University of Alberta, they have, I think, 4 or 5 different specializations for your undergraduate degree that you can follow. And like some of the big ones are astronomy, but you also have geophysics and a few other ones that you really don't get when you have 6 people in a class or on that order.
Hmm.
Also, a lot of fluid mechanics class are actually in like the mechanical engineering department. Even though they're basically learning the physics, right? But I think on the engineering side, there's much more bigger application compared to on the physics side, because most of the industrial applications are going to be on the engineering side compared to the physics.
Yeah, and then exactly like the counter argument to why you should do fluid mechanics is in your undergrad. Like you said, Pheely, it's just hard. Um, it's a lot of, oh, we can't do this, so we have to approximate things away, or just doing these really complex numerical things to solve something. It's very interesting though, right? Like it's funny how it makes sense to me now, but when you explain this like to someone who's not as inclined with physics, like we can relativity and quantum mechanics. I mean, combining them's a whole other deal, but on their own, they're kind of like simpler than fluid mechanics, which the first time you tell someone that, they're like, how can quantum mechanics be simpler than fluid mechanics? It's like, well, conceptually it's harder, but like mathematically it's way simpler because Navier-Stokes are brutal.
Well, what they say, like we might understand quantum mechanics before we understand turbulence.
Oh yeah, yeah, exactly, right. And again, when you tell someone that at first, they're like, how? But to like a physicist, it kind of makes sense because quantum mechanics, you've kind of boiled away all the hard stuff, and you're just left with a very simple system. You're like, oh, here's an atom, and here's another atom, and this is kind of how they interact. Whereas in like fluid mechanics, I've got like millions and billions and trillions of atoms all interacting in some way, and they're all at some temperature, so they're all vibrating a lot, and they're moving together, and there's like it's quite complicated. So it kind of makes sense that it's hard to model. So anyway, I did a bunch of other stuff this summer, but I learned a lot about fluid mechanics and this dam breaking problem, and I'm working on getting some papers out on it. Yeah, I like it. I like fluid mechanics. It's one of these things I didn't know I liked until grad school. A few years ago, I took a class on it and I loved it. So I've been slowly trying to put it into my research over the last couple of years, and I finally got it in.
Very nice. Speaking about research and stuff that was done over the summer as well, from my understanding, some certain members of this podcast, along with a former guest, actually published a paper, and it is now published, from what I understand, in September, was it? And it is available for you to view, and you can probably find a copy of or a link to it in the show notes.
Oh,
But do you want to tell us about that a little bit?
yeah. I don't know if me or Pheely should talk about. I'll start and then I'll hand it to him when it gets hard. So me and Pheely and our friend Dean, who was a guest on this podcast, who does like laser physics, but he used to do more computational stuff. Um, During our undergraduate, we all worked for a professor on density functional theory, which I'd say the three of us know very little about, but we somehow managed to write a paper on it and publish it. So it got through peer review, so we must know something. But um, anyway, the paper was more of like a mathematical proof than it was to do with density functional theory. But yeah, it was cool. We Dean messaged me and Pheely one day and said, "Hey, I think if we combined all of our notes from this work we did in 2017, like we could probably get a paper out on it." And I was like, "Oh, I don't think either of us all realized I think we all thought we had the same notes, but we all had like 1/3 of the puzzle, and then realized that we could put them together and finish the paper. So we did that, and we did a bunch of math, and then we talked to one of our old professor who passed away, who we did this work with. Um, we talked to one of his colleagues, and his name's on the paper now too, because it was his idea, and he did a lot of the original work with our old supervisor. So yeah, it, I don't know if we actually want to talk about the paper itself, but it's a bit of a doozy.
I mean, I'd certainly like to hear about it at a future time, and maybe we can get Dean back on so we can have the three of you uh, discussing it and really delving into it. And I guess as the challenge for you is trying to describe the concepts discussed in the paper in, I guess, a more friendly way than an actual scientific publication. Because, I mean, they can be, especially looking at that one, it's quite math heavy, of
Yeah.
course. And it's hard to describe equations, but if you can describe the general concepts behind it in a future episode, I think that'd be very good.
I can probably do it now, but I don't know.
Well, might be worth spending a main topic on.
I mean, I did try to give a little talk to my group about it. So in a sense, it's quite
Fresh.
quite chill, fresh-ish. My brain is not fresh right now. I'm a little sick. Maybe I sound a little nasal, but yeah. Well, the idea is to basically rectify one of the what's called overlooked. What do you call it, Liam? Overlooked. It's not even
I'd
inconsistency,
call it a
is it?
problem. I'd call it a problem in the literature that 1 to 6 people care about. Maybe at one point in their life they did, and they said there's this
Yeah.
thing, but we'll
Yeah,
ignore
there's
it.
a thing called density matrices that used to describe like a quantum system, and for us it's basic at low temperature, and we just started at zero temperature. So basically, no movement. It's totally quantum mechanical effect, and it turns out if you have a density matrix, it should be Hermitian because Hermitian matrix give real eigenvalues. And what does that mean? Real eigenvalues mean it's measurable. So anything you measured, the number is going to come out to be real. When you observed something and it's real, so you can measure it. So if eigenvalue is complex, then you can measure it. You can observe it. Things you cannot observe doesn't exist. Well, I mean, it doesn't manifest itself in a physical reality. So as scientists, we don't care about those things, right?
Well, you gotta be
So we
careful
want,
saying that.
well, I mean, as observers, we don't care about those things.
Yeah,
We can't measure it, right? So, but somehow when people derive this density matrix, it turned out one way is Hermitian and the other way is not. Even though in principle we know they all should be equivalent and they all should be Hermitian. So our paper basically showed a mathematical proof that with proper transformation and proper math, we can prove that in the dimensions or any dimensions, that all these density matrices are the same and they are equivalent.
yeah. Like you can't. The density matrix describes your quantum system, or like you're either a many body system or just a single system. In our case, it's a one body density matrix, so it's describing the quantum mechanics of a single. Is it a single fermion, or is it like a many body system of fermion? I
Well, it's a many body. Well, that's why it's a density matrix, right? So if it's
Yeah,
just a
but
single particle, it wouldn't be a matrix.
well, it's a one body density matrix though.
Yeah. So, well, you wrote this in the paper, but so the
I
point of one body density matrix is instead of having a multiple like n interacting fermions,
yeah,
you're gonna have one density matrix of non-interacting fermions instead,
yeah, okay,
right?
okay.
And you code your interactions in terms of the potential, like your effective potential instead.
Yes, thank you for reminding me about what I wrote. Honestly, yeah, a lot of that stuff kind of like it was in my head and I forgot it since. my contribution to this paper was mostly just math.
I mean, I think Kamal wrote quite a bit of it
Yeah,
too.
he came along and he saw what I wrote and was like, "That's half wrong. Like, fix it." The math was mostly me. Well, I don't want to say mostly me, but like, my contribution was the biggest part was the math. The kind of physics behind it I didn't fully get. I just know you start with this equation, you end with this equation. Uh, but anyway, yeah. So you have this one body density matrix that describes it approximately describes your many body system because it turns out for like in general you can't derive a solution, you can't derive an expression for this one body density matrix. You have to do like approximations to get it, and there's different approximations you can do, and there's all these different methods you can use to find approximate representations of your density matrix. And a subset of those methods are called semi-classical methods, where you get like a classical part plus a quantum correction. Um, and even for semi-classical methods, there's multiple methods, like sub-methods you can use to get a semi-classical density matrix. And exactly what Pheely said. So in the literature, some of those semi-classical methods are Hermitian and some of them aren't, even though you know they should all give you the same thing. Um, and it's kind of like an artifact of the mathematics you're using, and we showed them. I mean, it wasn't me and Pheely's idea or anything, but we helped show with our co-authors that it's just an artifact of the mathematics and kind of the coordinate system you're using, and one of them's more Hermitian looking than others, kind of. Um, I mean, as far as I'm concerned, it's like, I mean, the authors of paper normally shouldn't trash talk their own papers, but as far as I'm concerned, it's like such a niche little subtopic that like no one will ever care about it, as far as I'm concerned. But hopefully I'm wrong, and hopefully people appreciate it. I don't know. What do you think, Feely?
Well, I think all these human endeavor is collection of all these. There are big papers, and there are small papers that fill in the gaps, right? So you can't really have a complete, or try to get a complete picture of something, a model of something, without these kind of holes that exist all the time. When you publish, let's say a big paper, there's gonna be people who say, well, what about this case, and such. And it just turns out, I mean, our case is quite specific, right? It's like a 2D Fermi gas at low temperature. But well, there are holes, a lot of holes in the literature sometimes. Maybe not this case, but in the literature in general in science, and we need people to plug those holes. And it's nice that we kind of did that a bit. When someone may ask, in a class, well, when we see these density matrices, they don't look the same at all. Like, how do we know it's the same? The derivation is not the same. And they can point to our paper and say, hey, look at this here, boy. This is the same. Or girl.
Oh, that was the other thing our paper did. So at first I was pretty worried about like, would the refs accept the paper? Is it enough to publish? But then we got this little like bonus result out of the paper that I was really happy about. So our paper focused on like 3 different ways to derive a semi-classical approximation for this density matrix to describe your gas of fermions. And um, one of the methods was Hermitian. So no matter what you do to any order, it's Hermitian. But the other two, sorry, um, they're not Hermitian at all orders, which basically means like if you have an infinite amount. So yeah, the math gets pretty wild, but you have an infinite series, which means you add together an infinite amount of things. And if you add together an infinite amount of things, it was Hermitian. But realistically, if you want to use it in a calculation, you have to cut that off somewhere. For anyone who knows Taylor series, you can think of like, you can let the sine function, a sine wave, you can approximate it as a linear function plus a cubic function plus an x to the 5 function, and you can do that for an infinite amount of terms. But that's not realistic to use in the real world. You have to cut it off somewhere, right? So Yeah, so the other two
Well,
methods, when you cut them off, they're non-Hermitian. Um,
yeah. Well, I mean, what happens is that sometimes, let's say you have an even function, but approximate it, do a theory expansion on it. Not every term is gonna be even. Oh man, that's my guess. But maybe it's even. I'm wrong. But it's the same idea, right? Like where when you do approximations, if you do it in a specific way, you may lose certain properties of it because that's not the entire picture. But there's also a way to preserve certain properties that you need. In this case, hermeticity. And if you basically you said, Liam, like if we include all the term, all these infinite terms, yes, everything will be nice, but nobody can use infinite
yeah,
terms.
exactly.
So the fact that the truncation actually remove the hermeticity, we kind of have to show that, well, we actually can transform it into the form that preserve everything. Well, preserve hermeticity, and they're all equivalent just because in this form, it doesn't look like it does, or it doesn't. But it actually is just the same, but because just the truncation itself kind of removed that property that we required.
So this little bonus result was that in the literature, people had derived the non-Hermitian one for arbitrary d dimensions. So you might ask, why do you care about d dimensions? There's only 3 dimensions in space, x, y, z. It turns out that even though we were using spatial dimensions, when you do a lot of these density functional theory calculations, you can exchange like degrees of freedom. So in some cases, you can put in like extra dimensions, which could be like, I don't know, different modes of vibration or things like that. But essentially, people really like to derive these d-dimensional expressions and then put in some number for d. So in space, there's 3 of them. Maybe you can include time as a 4th one, and then maybe you can even include all these other ones. So you could have more than 4 dimensions. But just to be clear, like they wouldn't be more than 3 spatial dimensions. They'd be other degrees of freedom you'd account for. But anyway, the non-Hermitian method people derived, you can easily derive the d-dimensional expression, but the Hermitian method, where things are Hermitian and you get real numbers that you can measure and observe, people had only derived it up to 4D. So people derived it in 2D. I think like the guy we actually published with Kamal, him and his friends did it in 2D, and then they did it in 1D. And then in 2019, they had this, or was it 2021? I can't remember, but somewhere around there, they had a paper where they did it in, um, oh no, they did it in 2D and 3D. And then in 2021 or 19, I forget, they did it in 1 and 4 dimensions in a paper. And then they said, well, if you look at the 1, 2, 3, 4 dimensions, the d-dimensional expression is probably this. And because our method, we took this non-Hermitian one and transformed it to be the exact same as the Hermitian one, we actually like directly derived this d-dimensional expression from scratch. And it was the same one that the other authors had proposed. So we plugged 2 holes. We said, all right, this hermeticity issue's been solved now, and then this proposal for the d-dimensional expression this other paper gave is indeed correct, and we've shown that they're correct by deriving it from scratch. So once we got that little bonus result, I was super happy. I was like, I remember when I found that paper and I was reading it, I was like, oh, we can do that. We can do that, and that'll give us enough to publish. So I was pretty hyped about that. Publishing's a whole thing. I don't want to say it's political. That might not be the right word, but it's not easy. Journals don't want to take you if they don't think you're doing like good work, or you're not doing something significant enough.
Well, it's a form of gatekeeping, right? And some people can argue that it's bad, like the what's called the reverse
Well, we
archive,
had a whole episode on this in the last season, I think.
right?
We did
Right.
indeed.
So some people don't like peer-reviewed journals or peer review method at all. Like some people are some scientists are actually quite vocal against it, and maybe sometimes for okay reason. But I think you kind of need to have this, or anyone
Yeah.
can just publish whatever crap, right? And well, one thing to learn how to be proper scientist is how to you make your work acceptable in your field, or in any field that you want to publish in. And but like how you walk outside and you kind of have to wear clothes, right? There's decorum and there are rules.
Yeah,
So
it's like if you're publishing like blatant lies, you need like all the people who are angry at peer review, sometimes it's justified. I mean, you talk to most physicists and they all have like bad experiences, at least one bad experience with some editor or some ref that was just angry at them for no reason, right? Like it happens, but in general it's a good thing, or else like you said, you just get
well,
kind of crap.
well, science in a sense, like I mean, in its essence, is like a pursuit of truth. So people want to make sure that what you are publishing is truthful and your methods is not just some fallible or fallacy, right? So to make sure of that, so when it's public and when it's tied to your journal, let's say like your reputation, it is correct and acceptable as facts. And they have also like let's say like conference papers or like engineering journals and stuff too. And sometimes when you publish in like conference stuff, sometimes there's no peer review, and sometimes it's fine, especially like in well what I heard like say in engineering, because I think it's a more in a more practical regime when people can just like, well, I'm gonna build it. If it doesn't work well, I mean it's wrong, right? And sometimes in the physics is very difficult to replicate. If you look at data that come out from, let's say, Snow Lab, for example, yeah, right. If there's no one who peer review it and make sure that's like correct, like you gotta have one at Snow Lab, one Super Kamiokande in Japan. If let's say the two group are in cahoots, they could just publish anything, like, because who else peer review it? Probably there are people that they know, right? So there is the degree of integrity that scientists kind of have to hold when you peer review paper, because some experiments are extremely difficult to replicate. But we know that if it's gonna be something important in the future, someone's gonna replicate it. Like it's almost inevitable that so you don't want to ruin your name now nor in the future.
Yeah, it's certainly a worthy topic of discussion, and this was actually from season 5, the final episode, episode 70 of season 5, titled Scientific Literature Publishing and Gatekeeping, which you should definitely check out. We go a lot more in depth with how the publishing process works and some interesting details that surround it, and also other scientific documents that you might find on the internet that may be subject to a little bit more skepticism. But just in the interest of time, does anyone else have any other interesting updates that they would like to share from their summer before we move on to the last part of this episode? Okay.
I could talk forever. I got through like one project today, and I've got 2 to 3 more going on. Actually, 3 to 4, because I have the work I did with Peter Marsland during my undergrad is finally almost ready, or at least part 1.
Very exciting.
So,
well,
yeah, I better not. We need to do this in the future.
Yes, absolutely. Maybe one day we'll get Dr. Marsland on. But in the meantime, if you would like to hear some of our past guests from the Hyperthesis, you can listen to 84 episodes previously, a lot of which have had guests. If you're interested in becoming a guest on the show, if you're an expert in your field, somewhere in the realm of science, we would love to have you on. You can send us an email. We are hyperthesispodcast@gmail.com. You can also reach out to us over Instagram. You can find us at the Hyperthesis, where I don't know how many updates were done during our little bit of a break. I'm seeing a big fat 0 from Liam.
Yes.
But perhaps we'll get those updates back up and running, and maybe he'll really spoil us and post a nice meme relating to, I don't know, maybe something from this episode. You'll also have to check out our Instagram to find out. We are also reachable through a few other means, including through YouTube. So you can watch a backlog of our episodes from YouTube. I believe we're all updated up to the end of season 6. So you can watch our nice animations throughout the seasons as done by Pheely. A lot of work goes into processing those, especially. I don't want to know how many CPU hours have actually been spent on those episodes, but it's a lot. The other place where you can find us is wherever you listen to podcasts. So whether that's Spotify, Apple Podcast, YouTube Music, which is now the new home of Google Podcasts, or really wherever you get your podcasts. You can search up the Hyperthesis and you can find us, and make sure to share us with your friends. You can also find a link to our Spotify home base, I'll say, within the show notes, along with some other links that you might find interesting, including their new paper that they've published. So really, however you want to, feel free to contact us with questions or with topics that you want to hear. And we're really excited to start season 7. And there's a lot of cool ideas that we have planned and coming up for you. But we are always welcoming new ideas and new guests.
Yeah, by the time this, we're recording this, I don't want to say the date, but it'll probably be a little while before it gets published because we're going to probably get a little backlog of recordings done. But oh, okay, maybe I will give the date because tomorrow's the Nobel Prize in Physics announcement. So I don't know I don't know if you want to do a story, but first we can maybe do you know what field? Oh, do you think what field do you think the Nobel Prize will be given in this year for physics? I don't know if you guys know anything about any of this. I don't. I just have my hopes and dreams guess, which would of course be Michael Berry for the Berry geometric phase, which we may or may not talk about in the near future, potentially. Keeping it nice and vague. So I always want him to win the Nobel Prize. Again, will he? Probably not, but who knows?
I mean, that'd be pretty cool. And I don't see any particle physicists getting in it. I'm still kind of involved in that world, but probably not for this year.
Well, I haven't heard any like a huge breakthrough in particle physics lately.
Yeah, they've been doing a lot of like upgrades and stuff to the
in the next 10 years maybe, because the new data things start coming out and maybe there's something, who knows.
Yeah, I'm sure in the next 10 years there'll be like a particle neutrino or something like that Nobel Prize. Maybe 15. It kind of depends. I don't, again, Patrick, you know more about this than we do probably, but I don't know the timescales of these things very well.
Yeah, well, we'll see.
Long timescale.
Yeah, long timescales.
But, I'm always rooting for Michael Berry because that'd help my career a lot, honestly. So let's go Mike.
Well, on that note, so in lieu of a story today, instead, I thought it'd be fun to just kind of give a little bit of a science news update. So we've been gone for a few months, and there's been a lot that's happened over the summer, both with our own personal research and with research outside of our realms of interest. So I'm just I've handpicked a few different topics that I just want to share. Just here's an update from the world of science of, hey, what's going on right now, and what kind of interesting research is being done. And to start that, I will start with the current Nobel Prize that has been announced so far, and that's a Nobel Prize in medicine. So I believe that was actually just announced this morning, but the Nobel Prize in medicine was awarded to 2 scientists for their work on microRNA. So these 2 scientists are Victor Ambros and Gary Ruvkin for their discovery of microRNA and its role in post-transcriptional gene regulation. Now, I'm sure there's a lot to get into, but it's always a very, very big deal winning the Nobel Prize. And their work helped explain how, despite the fact that all of our cells carry the same DNA, they still produce different proteins and have different characteristics. And so, for example, your nerve cells are very different than your muscle cells, but they all originate from the same DNA. So there's this differentiation that happened. And so this idea of microRNA essentially introduced an idea of gene regulation. And so I wouldn't get too much more into that, but it's essentially a very interesting um, process that occurs that leads to this different selections and kind of divergence of your cells, even though they all share the same DNA. And we may be able to get into that in the future. But for now, moving on to another scientific discovery, not quite a world away, but pretty close to us, is the fact that the Earth has a new moon. So congratulations to the Earth on your brand new baby moon.
What?
So this is an asteroid that was orbiting the sun and has been fortunate enough to be captured within Earth's orbit. So we now have a new moon. It's very small, much, much smaller than the moon. You may not even be able to see it with the naked eye. And it will be around for the next about 2-ish months, I believe, because of the fact that we do have a moon and we have the sun and the Earth, and there's a multi-body problem going on. It's not in a stable orbit, so it will be ejected far out into space away from the Earth. But for now, we have 2 moons. So if you've ever wanted to recreate the binary sunset scene from Star Wars, this is a good chance to do that. Good luck, and I hope you have a really good zoom lens.
Copyright.
Copyright. In a little bit further away news, a really cool thing that was done was a flyby of a planet, specifically a flyby of Mercury. So in this case, it was a probe currently orbiting the sun. It's operated by both the ESA and the Japanese space program, and it's called the Bepi Colombo. And it is a mission to the planet Mercury. And it was actually able to perform the closest planetary flyby ever. And it went past the surface of Mercury at just a distance of 165 kilometers, which is, I mean, definitely lower than the altitude that the space station orbits the Earth. So it's really quite close to the surface, and it can do so because of the fact that Mercury doesn't have an atmosphere, so it's not burning up.
So Venus is the one that's slightly further away, and that one's got like some crazy dense atmosphere, right?
Yeah, it's a very thick, very carbon dioxide heavy atmosphere.
Yeah,
So
I watched like a YouTube video months ago about how people have been trying to land things on Venus and how they've slowly trial and errored their way into it. But so Mercury's got no atmosphere because it's so close to the sun. Okay.
And also it's smaller, so most likely no magnetic field. But there are like the messenger probe, which are trying to determine what exactly is going on with Mercury. In other space news, China has been in the space news a lot recently with a bunch of different launches. So they were able to land successfully a robotic probe on the far side of the moon that began a sample collection, and it was actually able to return that sample of 2 kilograms of cargo on June the 4th. So right before we kind of finished recording, but still kind of happened in that time zone. Further afield, astronomers have identified the slowest spinning neutron star. So typically they spin quite quickly at many times per second, but this one rotates at just once every 54 minutes. So there's a couple different explanations as to what happened here, but either it was an incredibly slowly spinning star, or because of conservation of momentum, it could have been 2 opposingly rotating stars or neutron stars or something like that combining, where it has slowed down enough that it takes 54 minutes to rotate. Now, of course, this is much faster than the Earth, which takes 24 hours, but it's still quite slow. Moving on to kind of the biology-related field, we have the first mouse model with a complete functional human immune system. So mouse models are used in living creatures that are not human, so in non-human species, but designed to mimic human functionality in different ways so that we can better understand their biological phenomena without actually studying humans themselves, which can get very dicey. So they were able to make a mouse model of a functional human immune system, which is really cool. So now we can, it allows us to better explore the immune system itself, including different autoimmune diseases, as well as how it reacts to different things, and may lead to very interesting research in the future. Moving over to what might be inside your house right now, not to scare you at all, but your dogs might be dreaming of you. There was recent studies on essentially what dogs do when they sleep, and it's been shown that they do actually have rapid eye movement, meaning that their brains are still active while they're asleep, and they're most likely dreaming in some sort of way.
I thought people knew this for a while. Maybe not scientifically, but like, people who have dogs, you can see them like sometimes you see them doing things in their sleep that are like obviously they're trying to like run or something in their sleep, or I don't know, like I thought people maybe like had experience with this before and maybe they just hadn't scientifically tested it. Maybe I'm wrong.
Yeah, and it appears that this is a kind of a further advancement on research that's been done. So particularly by Deidre Barrett, who was the author of the Committee of Sleep, who kind of talked about what our pets might or might not dream about. And chances are they more likely dream about simpler things than what we have, which are like very vivid hallucinations for some people, but more so like smells that they smelled on a daily walk, or kind of simpler concepts like that.
Yeah, like my cat's had nightmares before where we're just sitting there in complete silence and he'll just wake up on the other side of the room and start hissing and looking around frantically. And I'm like, I'm pretty sure that's a nightmare. Maybe his ears heard something I can't hear as a human, but it feels nightmare-y. So cats will be the next study for them. Maybe they'll move on to cats after dogs.
That'd be very cool. Speaking of cats, though, it was found that cats are evolutionarily perfect. So that being in the sense that no matter what kind of cat you're looking at, so whether that is a common house cat or a wild cat, such as like a tiger or a leopard or things, or different types of cats, they're pretty much virtually identical in terms of their carnivorous diet and also similar bone structure. And this really isn't seen across any other species, especially with mammals. So, for example, we have different types of bears that exhibit different traits and different food types. But with cats, they're pretty much identical. And it's quoted from Anjali Goswami, who's an evolutionary biologist, that cats are not jacks of all trades. They are truly the master of one. So they've perfected their form, essentially. As just kind of a final few things, if you've been paying attention to space news, we have 2 astronauts are stranded in space due to issues with the Boeing space capsule that brought them up in the first place. So an 8-day mission has now turned into what's predicted to be about an 8-month mission, which will be very interesting to study, considering the astronauts have been to space before, and some of them are undergoing very extreme effects, and we can better study long-term exposure to microgravity as well as increased radiation from outer space. So there's a lot of very interesting things going on within the world of science. Of course, as Liam said, we'll be figuring out what the Nobel Prizes are for the different fields, including chemistry and physics, and we'll see if his prediction is correct. But yeah, this is just a minor update on just a few headlines from the world of science. And as one more update, just a bit more local, but not local, there's a researcher at the University of Alberta. His name is Dr. Chris Hurd, and he just recently published a paper looking at Martian meteorites. So these are meteorites that are originally from the surface of Mars that were ejected into outer space and eventually have landed on Earth. But through some very impressive work done by him and collaborators, he was able to identify with a good level of confidence where exactly on the surface of Mars these meteorites have come from, down to the crater, which is really quite impressive investigation work. And there's a lot of simulation and analysis work in there, but just something very cool that's a little bit closer. With that,
I say thank you very much for those stories, Patrick. The quick science update was very good.
Thank you. And with that, we will turn it to Pheely quickly.
Well, one thing I kind of want to mention, maybe just kind of random, but I remember that people just like to say, like we know a lot more about the surface of all the planets. We have the map of surface of all the planets than we have of our ocean. And it sounds fun when you say that, but like I bet if all the planets have the ocean, we wouldn't have maps of what under the ocean either, right? So it's like compare apples with oranges. So that's kind of funny statement to me when I hear it.
It's like you said, Pheely, fluid mechanics is hard.
Yep.
Well, with that, we will wrap up the first episode 85 of season 7. Again, we have a lot of exciting things coming through the pipeline, including talking about some more battery talk, which is pretty exciting, and advancements with that, along with a host of other guests and other topics. So stay tuned, and we'll see you next time. Bye, everyone.
Take care.
Audio.